Hello friends, welcome to the YouTube channel of SND Engineering College and Research Center Eola. Myself, Professor Harish Bhangare. So today in the online lecture series, let us discuss the topic of basic electrical engineering of first year, that is on electromagnetism. So today we will cover magnetic effects of electric current, magnet and magnetic field due to current carrying conductor. So to study the magnetic effects of electric current, we have to first see the conductor. And when we allow the current through a certain conductor, then what's the magnetic effect that cause that we have to see. But before that, we must know what is magnet and what are the different properties of the magnet. So the magnet is nothing but a piece of a solid body which possesses property of attracting iron and some other metal pieces. So whenever a magnet is there, whenever the word magnet comes, that time we know that it attracts, and it attracts all the time the metals. So the property of attracting is nothing but the magnetism. And the lodestone is a naturally occurring magnet. It attracts material like iron, nickel, cobalt, etc. Now, such a magnet is rolled into iron pieces. It will be observed that iron pieces cling to it. Whenever we roll the magnet on a iron pieces, that time what happens? That iron pieces will be attracted toward that magnet and will adhere or cling to its surface. So the points at which the iron pieces accumulate maximum are called poles. You will observe that iron pieces will concentrate more on the ends of the magnet. Means that iron pieces will less at towards the center, but more density of iron pieces stuck is towards the end terminals, and that are nothing but the poles. So the poles of the magnet, while imaginary lines joining these poles, is called axis of the magnet. When such a magnet is suspended freely, if you suspend this bar magnet in the air freely by a piece of silk fiber, it turns and always adjusts itself in the direction of north and south of the earth. Means the magnet is always suspended in the direction of the geographic north to south. One of the law of the magnetism is like poles repel and unlike poles attract. It is just like the charges, the positive and negative charges. The poles attract and repel. Like poles repel, while the unlike poles attract each other. So here the two unlike poles are there, north pole and south pole. They are bring together. So what you observe, there will be the force of attraction in between them. But if we bring together north pole with the north pole of the other magnet, then there will be force of repulsion is there. Now a bar magnet is a rectangular object composed of iron, steel, or any form of a ferromagnetic substance that shows permanent magnetic properties. It has two different poles, a north and a south pole, such that when suspended freely, the north pole aligns itself towards the geographic north pole of the earth. Now let us see what is the magnetic field. The region around a magnet where its magnetic influence can be experienced is called a magnetic field. Now it is not possible to see the magnetic field by your eyes. It is not visible, but we can experience that there exists a certain magnetic field. So the direction and strength of a magnetic field are represented by magnetic lines of force. So here, these are the magnetic lines of force. The lines of force comes out from North Pole, means originates from the North Pole and will terminates or enters into the South Pole. Now, for experiencing the magnetic field around a bar magnet, let us put the bar magnet on a paper, and on that paper, the iron filling is there. Now, as soon as we put the iron on the iron filling, that iron filling will adjust themselves in such a manner that they will form a concentric circles like this. They will form a concentric circles like this. And this arrangement of the iron filling itself is only due to there exists certain force, magnetic force is there. And these alignments on the concentric circles are nothing but they represent the magnetic lines of force. They represent magnetic lines of force around the magnetic substance. Now, the magnetic field lines result in the formation of continuous running closed loop. If you observe these magnetic lines of force are a continuous closed loop, they will form a continuous closed loop. Means from north pole, they will emerges out externally, go to the enters into the south pole, and internally in the bar magnet from south to north. Like this, they will form a closed loop. The tangent to the field line at any given point indicates the direction of the total magnetic field at that point. Now here one compass is placed. The needle of this compass will direct in this direction, and this direction is nothing but it is towards the tangent of this circular path. So the greater the number of field lines crossing per unit area, the higher the intensity, the stronger the magnitude of the magnetic field. Means as the density of the magnetic lines of force is more stronger is the magnetic field. In other words, we can say that also if we move towards the bar magnet, the magnetic field increases, and as it goes away from the bar magnet, then magnetic field decreases. So there is no interaction between the magnetic field lines. That magnetic n number of magnetic field lines are there, but they never intersect each other. And we can say that is the property of the magnetic lines of forces. The magnetic field lines for a closed loop. Since magnets have dipoles, now magnet consists of two poles. That's why it is called as the dipoles. So magnetic field lines must originate and end. Therefore, by convention, it starts at the north pole and moves towards the south pole outside the bar magnet, and from south to north pole inside the magnet. Hence, it forms the closed loop. Now, no two magnetic field lines are intersect. Magnetic field lines do not intersect as there will be two tangential magnetic field directions associated with the same point, which does not occur. If a compass needle is placed at that point, it will show two different directions of the magnetic field, which is absurd. The relative strength of magnetic field infer from magnetic field lines. The closer or denser the magnetic field lines, greater is the magnetic field's strength. If the density of the magnetic field lines is high, then magnetic field strength is more. If we are very close to the magnet, then again the magnetic field is strengthened or more. Now, the next topic is magnetic field due to current carrying conductor. Now, whenever a current carrying conductor will observe, when a current is flowing through certain conductor, and if a certain magnetic compass comes near to that conductor, they will observe certain deflection in that compass. And why so far the compass deflects? Obviously, there must be certain magnetic field. So when the electric current flows through a current carrying conductor, it produces a magnetic field around it. So this can be seen with the help of a magnetic needle, which shows deflection. The more the current, the higher is the deflection. If the direction of the current is reversed, the direction of the deflection is also reversed. And this experiment is performed a first time by Oersted. And that's why this experiment is known as the Oersted experiment. So in the first figure, you will observe that the switch is open, battery is connected to a conductor, but switch is open, the circuit is not complete. That's why the magnetic needle placed aside to the conductor, it doesn't show any deflection. It settles in the north to south direction of the geographic poles. Now, as soon as I close this switch, that time current start to flow in this direction. Current start to flow in this direction, and that time you will observe the certain deflection in the compass. Again, if I change the direction in this third figure, I change the direction of the current. So in that you observe that the deflection of the compass is in the opposite direction. Means there exists, as soon as the current passes through a conductor, that time there exists a certain magnetic field, and that magnetic field has a certain direction, and that direction depends on the direction of the current flowing through the conductor. Here the direction of the current is in this direction, that's why the deflection is in a clockwise direction. Here the direction of the current is reverse, so again the direction of the deflection is anti-clockwise direction shown by the compass. So it proves that there exists a certain magnetic field around a current carrying conductor, and this is the magnetic field due to a current carrying conductor. Now here the experiment is conducted to visualize. It is not possible to visualize, right? We can't see it, but experimentally we can experience, right, that the magnetic field exists around a current carrying conductor. So here a straight current carrying conductor wire is there and is threaded through a plain paper, and on that paper iron filling is there. As soon as I started this switch and allowed the current to flow through this carrying conductor, that time a certain magnetic field exhibits around this current carrying conductor. In second figure, you will observe that current is flowing from bottom to top. That time certain magnetic field generates around the current carrying conductor, and the iron fillings placed on the plain paper, they rearrange themselves in such a way that they will look like a concentric circles. They will arrange in the form of a concentric circle, and these concentric circles are nothing but the magnetic lines of force. So it proves that there exists a certain magnetic field around the current carrying conductor. So in this way, you can visualize that magnetic field around the current carrying conductor. So certain questions on this topic are there. You should know the answer of this. So what is magnet? What is magnetism? State laws of magnetism. State the properties of the lines of forces. So you go through books and prepare this topic well. Thank you. Thank you very much.